Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through this chemistry 5070 end of year assessment. This is just for year 9 in a 3-year program. So obviously there are only a few topics that have been covered so far. These include the kinetic particle theory, which involved the states of matter. And then we also did atomic structure. So all those protons, neutrons, electrons, isotopes, and then we did bonding. So structure and bonding. After that, what else did we do? We did mole calculation, so stoichiometry, ratios and limiting access, that kind of stuff. And finally, the last topic that we did in year 9 was experimental techniques. This includes all the separation techniques as well as chemical analysis. So all the practical studies on the test for cations, anion, flame tests, as well as tests for gases. So these are the few topics that are assessed within this year 9 end of year assessment. So if you've done these particular topics, you might find this tutorial useful, and you can always pause the video and try the questions out yourself before you actually check the tutorial explanations. Okay, so this was set to be a 1 hour 45 minutes due to the new syllabus changes for the 5070. So the new paper 2 is now 1 hour 45 minutes for 80 marks. However, due to the limited topics that we have done, we don't have section B where the students can choose the options as to which questions to answer. So therefore, as an alternative, I actually slotted in some alternative to practical questions in the latter part of this paper, just to fill up the marks. Let's get started on the actual chemistry. In this first question, we have element X undergoing the following physical changes. These are changes of states of matter, so going between interconversion between the solid, liquid, gases. They're given us one, which is from liquid to gas, there's boiling or evaporation. We're supposed to put down the scientific name for each of these numbered physical changes. For 4 marks, this is quite an easy start to the questions. You really don't want to be losing any marks at all. So solid going to liquid, that is just melting. And then for number 2 is from gas going to liquid X, so that is condensation. Number 3, from liquid all the way to solid, so that's just what you do when you do freezing. Last but not least, this is probably one of the more difficult ones, but it is in your syllabus. Solid X going to gas straight away. This is direct. So solid going to gas is what you call sublimation. So think about stuff like iodine, which I have shown you and demonstrated to you in the lab, okay, long time ago. This is a gray solid. What happened then is you get a purple vapor, you get a purple gas. That was just in a test tube, the solid vaporizes straight away. Another example would be your CO2 solid. This is a dry ice. They call this dry ice. They use in theater, they use in movies, they use it in the fire extinguisher. It's present as a pressurized gas in the form of a solid. And then what happens is it goes to carbon dioxide gas straight away, which of course is a colorless gas, and you can't see colorless gas. So there's just sublimation there. To the next part of the questions. One difference between boiling and evaporation is how fast. Rate is to do with how fast. There's the English meaning of it. In science, we obviously know rate is monitored by how fast this gas is escaping, essentially. All right, how fast the liquid goes to gas. So one other difference, so it has to be other difference. We know that boiling only takes place at boiling point. Evaporation is at any temperature. Think about your clothes drying out on a hot day. So boiling cannot take place at any other temperature. It can only happen at the boiling point. At the boiling point, as you know from the heating curve, boiling point is when the temperature remains constant, goes from liquid to gas. You're overcoming intermolecular forces if they are simple covalent molecules, okay? And then what happens is evaporation can take place at any temperature. Evaporation takes place at any temperature. So this is a kind of question where you really have to specify details for both of them, because they're not just asking about boiling, they say boiling and evaporation. So we have to really specify how are they different between the two things there. Remember, you are not writing a marking scheme, you are writing an exam, and therefore your job is to show the examiner you know what you're talking about. Okay, do not even think what the marking scheme will say, because you never have a marking scheme in your real life, in your real exam. Okay, now the next bit for 3 marks, this is just describing separation, arrangement, and motion. So 1 mark for each in the solid state. I'll start with motion. So we know that solid particles only vibrate about fixed position. They only vibrate about fixed position. And then in terms of arrangement and separation, we know that solid particles are arranged very regularly. So regular arrangement, regularly. So they're very disciplined kind of arrangement where they stack one upon each other. In terms of separation, we don't call them closely packed. In fact, we call them tightly packed because they are very tight to each other. They're like touching each other, tightly packed. Okay, so touching each other with no space in between, no space in between, no separation, no space in between. Oops, sorry, I beg your pardon. No space in between. So basically they're touching each other there. They are packed regularly. They only vibrate about fixed positions. Now to the next one, we have a group 1 metal. We know group 1 metal loses 1 valence electron, 1 electron in the outer shell. What happens is it becomes X+1 cation. And you have an oxide because you react with oxygen. So oxygen exists as a diatomic molecule. These are from your structure and bonding. Oxygen has 6 outer shell electrons, being in group 6. So what happened is it shares only 2 outer shell electrons to give you a double covalent bond. That is the molecule. It exists as an element, as a diatomic molecule. But then what happened with oxygen is that the atom itself is to 6 electronic configuration. When you form ions, the atoms, not the molecule. The molecule has to go into atom by breaking up the covalent bond. And once you get the atom has to gain 2 electrons to become O2 minus ion, which now have fully filled outer shell. Fully filled outer shell, there's the main objective. You're trying to get to that stage when you can form a bond, whether you are forming a covalent bond, whether you are forming an ionic bond in this case, because between the metal and the non-metal. So what you have is X, and then you react with oxygen, and then you get X2O. And our job is to balance any questions, because whatever you write in chemistry, if you don't balance it, you know the game is over. All right, so there's only 1 oxygen, there's 2 oxygen, so I put a 2 in front, and I've got 4 X there. I cannot change the identity of X because it's a metal, it's not diatomic. Every equation you write has to be balanced, whether the question asks you to or not. In these next questions, we have noble gases. So we know noble gases are in group 8. We know that they have a fully filled outer shell. And as a result of the fully filled outer shell, they don't like to form bonds. They don't like to bond at all. So therefore, they exist as monoatomic. Monoatomic means single atoms. So these all exist as single atoms, as an element. All right. So as an element, they are not diatomic. Give 1 similarity in the atomic structure of these isotopes. So this question is basically a 2 marks question on the definition of isotope. Definition of isotope as stated in your syllabus. They refer to atoms of the same element. Obviously you can see radon and radon. Atoms of the same element with the same number of protons. So similarity is they have same number of protons, and then your differences will be the second part of that 2 marks definition. Atoms of the same element with the same number of protons, excuse me, but different number of neutrons. So what is different is different number of neutrons. How do I know the neutrons are different? Because if you look at the nucleon number, the nucleon number is different. And if the nucleon number is different, but your proton number is the same, so nucleon number is equal to number of protons plus the number of neutrons. If your number of protons is the same, then it means your number of neutrons must be different because you get a different nucleon number. Those are all your basic definitions, basic ideas from atomic structure topic. Next question. So we know that we say noble gases don't usually form compound, but xenon is one of those special things according to this question. So this contains xenon, oxygen, and fluorine. They give you the percentage of oxygen by mass, percentage of fluorine by mass. So we have xenon, we have oxygen. Let me just put in oxygen, and we have fluorine. So this is 22.1%, this is 17.5%. So this is the remaining bit. So make sure you can do the math correctly. So the sum of that 22.1 and 17.5, take it away from 100. So 22.1 plus 17.5 give me 39.6. And then I take away from 100, I get 60.4. Make sure that these things add up to 100% because there are only three things there. So this is actually percentage by mass because percentage is out of 100. So this is my mass out of 100 gram. I will label my step because label is important, not just for you to check your answer, but also for the examiners to actually check your work. I need to have a look at the periodic table. Hey, give me a minute. So from a periodic table in group 8, xenon has a relative atomic mass of 131, so 60.4 over 131, 22.1 over 16, 70.5 over 19. So evaluate these on your calculator. So write down the value because you want to show the examiner you know what you're talking about. So that gives you 1.38. 17.5 divided by 19, so they give me 0.92. All right, so at this stage I want the simplest ratio, so I divide by the smallest number. So the smallest number there is 0.461, so it's just 1. By right I should put down 0.921 I guess, but anyway, doesn't matter that much. So what do I have here? 0.921 divided by 0.461, I get 1.998, which is roughly 2. 1.38 divided by 0.461, I get 2.99, which is roughly 3. So I guess that is XeO3F2 then. Let me just double check. 1.38 divided by 0.461, that's 3. 0.92 divided by 0.461, that is 2. Yep, I think that is the simplest whole number ratio. Empirical formula defined as the simplest whole number ratio of the atoms. So that is XeO3F2 as your empirical formula. So in the next part of this question, so we have a sample of neon, which is a gas. It occupies the volume of these at room temperature and pressure. So this is described and explained using kinetic particle theory. What happens to the volume of the sample. So previously in our lessons, I already talked a little bit about this. This is to do with volume and temperature. This is to do with something called Charles' law. But we cannot just say Charles' law here because they say using kinetic particle theory. Charles' law is basically something you will have learned in physics as well. However, in our syllabus for chemistry, so it's just qualitatively describing and explaining in terms of what happens in terms of the particles. Okay, so Charles' law basically says that volume of a gas, so the volume of a gas is directly proportional to the temperature of the gas in Kelvin. Okay, however, like I said, you cannot quote this, all right, because they want it in terms of kinetic particle theory. So at constant pressure, so we are not allowing the pressure to change. What happens as temperature increases? As temperature increases, you could imagine when you have a balloon and then you put it in a hot boiling water, and then the balloon will expand because the volume increases. All right, so we need to explain in terms of what happened, describe and explain. All right, so the particles will gain more kinetic energy. So temperature is a measure of your average kinetic energy, so they will gain more kinetic energy. And when they gain more kinetic energy, they move faster. So the particles move faster, they collide on the walls more often, push onto the wall of container, more often. So like in the case of the balloon, the gas particle inside the balloon, they push upwards onto the balloon walls. Therefore, volume increases. So that is basically the kinetic particle theory explanation for Charles' law, which basically describe it in a mathematical equations. The next one is to do with changing the pressure by keeping temperature constant. This is actually Boyle's law. Just like the previous question, we cannot just state the Boyle's law without explaining it. This is an inverse proportional relationship. You will learn more of this in physics. Physics care more about the equations and the calculations and the graphical bit. Chemistry cares more about kinetic particle theory, what happened at the molecular level and the particulate level. Okay, so again, describe and explain. So what happened is at constant temperature, as we increase the volume, as we increase the pressure, we are kind of like squeezing the particles closer together. So the particles are squeezed. Well, not really squeeze. This is what we're doing on the outside. The particles get closer together. As we are exerting force on the walls of the container, right? So the particles get closer together. Therefore, the volume will decreases. Okay, so that's just basically Boyle's law. As the pressure increases, the volume will decrease. 1 over smaller will give you bigger pressure. Last bit of this question is a mole, well, it's kind of related to the mole calculation. This 21 DNQ sample of this gas is actually at room temperature and pressure. If it is at room temperature and pressure, we can use the molar volume of gas, which is 24 dm cubed. So that is the volume of any 1 mole of gas at room temperature and pressure, 25 degrees Celsius, 1 atmospheric pressure, 1 atm pressure. Anyway, you want to find answer to 2 significant figures. So the first thing I will be thinking about is I need the mass, and neon is monoatomic, so they are not diatomic. So I can imagine that the mass over the AR, because it's an element, the mass of the neon divided by the AR is going to be the mole of the gas, and this is equal to the volume of the gas divided by the molar volume of the gas. I have the volume of the gas in dm cubed. I can divide by 24 dm cubed per mole at room temperature and pressure to give me the mole of the gas. I can relate it to the mass of the gas and the relative atomic mass, just like that. So what I do then is I have 21 dm cubed divided by 24 dm cubed per mole. The unit will make sense because mathematically speaking, that is what we are doing. If you look at your periodic table, the relative atomic mass of neon is 20. So that is the mass of neon in gram divided by the AR, which is 20. So the mass of neon is going to be 21 over 24 times 20. So quite a straightforward question. It's not the first time you've seen this type of question. You have actually seen this in, one of your lecture tutorial exercises. So I actually went through something similar previously, but obviously it won't be the exact same question that will come out in exam. It's more about the skills, yeah? On to question number 3. So we have magnesium, calcium, and strontium. So we know group 2 start from beryllium, magnesium, calcium, strontium, barium. And this is N, this is the shell number. So there's 2, 3, 4, 5, and 6. Because the first row consists of hydrogen and helium only, there isn't a metal in group 2. So the first one start from group 2. The first one start from second period. So this is the second row, second period or period 2. So it's the second shell that you start to fill up. So when you have calcium atom, in the atom, number of protons equal to number of electrons. When you have atom, so what happened is in a calcium atom, your atomic number is 20. So, there is 20 protons, therefore there is 20 electrons. If you follow the periodic table, hydrogen to helium, the first shell 2 electrons, lithium to neon, second shell at electron maximum. You still haven't reached your target, which is calcium. Sodium all the way to argon is another 8 electrons. Now you're at argon, and you're very close to calcium, but you fill in the new shell, the fourth shell. Group 1 potassium and then group 2 calcium, just 2 electrons to get there. 2 plus 8 is 10, plus 8 is 18, plus 2 is 20. There are 20 electrons in an atom of calcium because there's 20 protons in an atom of calcium. Next up, describe how the arrangement of electrons in a strontium atom. How is it similar? How is it different? You should know that strontium is just below calcium. Since they are in the same group 2, in your atomic structure topic, the syllabus says candidates should be able to understand that group number tells you the number of outer shell electrons. So similar would be same number of valence electrons. They both have the same number of valence, or you can use outermost shell electrons, i.e. 2 valence electrons, because they are all in group 2. 2 valence electrons, group 2. Okay, how is it different then? We know also that strontium is in the new shell, further than just below calcium. So calcium fill up to the 4th shell, strontium fill up to the 5th shell. So therefore strontium has one additional inner shell compared to calcium. So strontium atom has one extra. You can use the word extra, or you can use the word additional, whichever one you like to use. Fill is filled with electrons, and this is called inner shell. Then calcium atom. Okay, it's not enough to just say that it has one extra shell, but of course that shell is filled with electrons, as you have to fill in the 4th shell before you go to the 5th shell. Okay. Part C is reactivity of calcium with water. So we did this when we did the couple of those general equations. Metal plus water give you metal hydroxide as well as hydrogen gas. However, this question is very nice. It's trying to lead you to that conclusion. So hydrogen gas is obviously diatomic molecule from your covalent bonding and from covalent bonding topic. All right. You get a colorless gas which pop with a lighter splint, so obviously it is going to be hydrogen. The reason why I don't write down the formula here, and formula will not be accepted here, is because if you read the question, it says name the gas. Okay, name the gas. They don't say give the formula of the gas. The next one, identify the ions. They didn't say name the ion. They didn't say give the formula of the ions. Identify the ion means you could give the formula, you could give the name, and it has to be ions. And this is for making it alkaline or basic. And we talk about it, pH greater than 7 is due to the hydroxide ion. So you can write down OH minus, or you can write down hydroxide because they never specify name the ion or give the formula of the ion. Hydroxide, OH minus, you cannot give calcium hydroxide formula because they want the ion. Next up, write a chemical equation. They didn't say it should be balanced. If you look at the marks, 2 marks, no equation that you write, in chemistry, whether you're in O-level or A-level or higher education, no equation that you write can be left unbalanced. All right. So what happened is calcium plus water give you calcium hydroxide. Calcium hydroxide, Ca2 plus OH minus. The minus charge refer to the all of the hydroxide. The OH has that overall charge -1. You look at the valency. The valency refers to combining power. For ions, it just comes down to the value of that charge. So 1 goes this way, 2 goes that way. What this means is there's 1 calcium 2 plus and there is 2 OH minus. If you count the atoms correctly, you should get calcium OH twice, which is correct. A lot of students just write like this, which is wrong, because you only have 1 oxygen, whereas you have 2 oxygens, 2 hydrogens. The -1 become -2, cancel out the +2 charge. The use of bracket is very, very important, especially understanding formula. These are very, very basic chemical formula. You can never get them wrong at all. And then obviously we get hydrogen gas. Hydrogen gas exists as a diatomic molecule, as I mentioned. Covalent structure and bonding, hydrogen atom, incomplete outer shell electrons. Instead, they share 1 electron with another hydrogen atom to give you diatomic molecule. Diatomic element as well. Diatomic, 2 atoms bonded together by covalent bond. We need to balance this equation. We got 2 hydrogens, another 2 hydrogen. We got 4 hydrogen total on the right hand side. We need 4 hydrogen atoms on the left hand side, and then they should give us 2 oxygens and 2 oxygen. They haven't asked for stat symbols, so we really don't have to write down the stat symbols at all. Question 4, we have this question on dilute sulfuric acid. You get salt from acid. So remember that salts come from acid. Salts are formed by acids. So hydrochloric acid from chloride salt, sulfuric acid from sulfate salt, and then nitric acid from nitrate salt. So we have 3 steps to make zinc sulfate from zinc carbonate. You should know that all your group 2 carbonates. Yes, I'm aware that zinc is not from group 2, but all the group 2 carbonates, MCO3, they are insoluble in water. We did this concept when I asked you to write down the solubility rules from the syllabus, from later on in the syllabus under preparation of salts, but we already know about solubility stuff because we went through it as we went through the ionic equation topic a couple of months ago, and I keep on highlighting them as we went through qualitative analysis topic. Yeah, so this including the Zn2 plus and the Cu2 plus carbonate as well, okay, for the group 2 carbonate insolubility. So we started out with something insoluble, and we get this zinc sulfate which is soluble. That's why we can filter the mixture, and then we hit the filtrate, because filtrate is the solution containing ZnSO4 aqueous, because that is soluble. And then there is this word called saturated solution, and in fact that is what is asked by this question later on, what is meant by saturated solution. So we'll talk about it later on, because this is part of crystallization. We are not heating it to dryness, not evaporation to dryness. So there are 2 different kind of techniques here. So what observations would you see to indicate that the reaction is complete? We have a carbonate plus acid. So you know carbonate and acid, you will get salt, you will get CO2 gas, so you get effervescence, because there is the test for carbonate in the lab under qualitative analysis. And therefore, when we use excess of this solid, which is insoluble, with all the acid, when all the acid has been used up, no more H plus, which come from the acid, which make it acidic. The H plus make it acidic. When there's no more H plus, then obviously there will be no more carbon dioxide being produced, because there will be no more reaction to form the salt. So therefore, when there is no more effervescence, effervescence is a term that you would have heard or that you would have known from your qualitative analysis under test for carbonate. Carbonate plus acid give you effervescence. It means rapid bubbling. Okay, no more rapid bubbling of gases. So effervescence refer to bubbling of gas, because you know there's no more gas being produced. You cannot say when there's no more carbon dioxide being produced, because carbon dioxide is colorless, so you cannot see carbon dioxide. You cannot say when there's no more carbon dioxide being produced. Okay, what do you see? The next one, which is very obvious, is to do with the insolubility of that carbonate. We use excess of these, so obviously when no more of the solid, because it's insoluble, or you can say insoluble zinc carbonate, so Zn2 plus CO3 2 minus, so insoluble ZnCO3 dissolve, or actually reacts or dissolve, because when they react they will dissolve as they form the salt, which is soluble. So no more of it will dissolve, they just remain, the solid just remain unreacted, just like that, because it's in excess. Then why is it important to add excess of zinc carbonate? Well, because we know that it is insoluble. So it is insoluble solid, and then we want all the acid to react. We want all the acid to react, and our salt is soluble. So we can remove it. We can remove the excess zinc carbonate, which is insoluble, at the end of the reaction. What is meant by saturated solution? This is stated in the syllabus as well as in the learning outcome. Whatever that the Cambridge syllabus stated, it means that they can ask you whatever they have stated, they have told you 3 years in advance. Okay, so we hit until the solution is saturated. It means it's a solution containing the maximum amount. It's a solution containing maximum amount, maximum concentration. So I think this is the word they use in the syllabus. Whether you use maximum concentration or the maximum amount, they'll be all right. It's of a solute. So you're dissolving a solute in a solvent. Very important. And this is also very, very important, is at a given temperature, because we know that solubility can change with temperature. Think about your syrup. When you go to higher temperature, you can dissolve more and more sugar, and then when they cool down, they get very, very sticky. It's the idea saturated solutions. When you heat up the solvent, most of them evaporate until the solution becomes saturated, but no solid appear yet. Yeah, okay. So what happens is when it cools down, the solid will slowly crystallize out as solubility decreases with lower temperature. As temperature decreases, the solid will come out as crystals, and you can collect those things with filtrations of the solid crystals that you form afterward. Next up, what do we have? We basically have a titration experiment. The experiment is called titration, but the reaction is neutralization. Titration is experimental technique. Titration is not the type of reaction. The type of reaction is between the acid and the base. So this is the base, this is the acid. The base, because it's a OH minus aqueous, and then you have H plus aqueous, and then you get H2O liquid. This is the ionic equation for any neutralization reaction, base plus acid giving you H2O liquid. All right, we have a methyl orange with a base. These are straight from your alternative to practical practice when we did mole calculations topic. So in a base, methyl orange is going to be yellow. At the end point, methyl orange is orange. When it's acidic, it's going to go red, very reddish or kind of pinkish. Okay. Question 5 is straight onto mole calculations. So we have this equation here. We want the maximum volume of the gas. So nitrogen is a gas. So we have to use this molar gas volume, which is given in your periodic table. You should know anyway, 24 dN cubed for any 1 mole of a gas. And this is only at a particular temperature, 25 degrees Celsius, 1 atmospheric pressure. Room temperature is 25 degrees Celsius, 29 Kelvin. Pressure, room pressure is 1 atmospheric pressure. This is a volume. This is a volume of solution. Do not confuse solution and gas, and be aware that this is concentration. Concentration is in mole per dN cube. When you do N equal to CV, the V has to be in dm cube, as the C is in mole per dN cube. This is mathematics. This is normal physics. We are just using this kind of things in chemistry, so you need to be very good with those unit conversion. So what do we have here? We want the nitrogen, and we can relate it to the ammonium nitrite. The nitrite ion, NO2 minus, is different from the nitrate, which is NO3 minus. Okay. From the balance equation, I have labeled it like this: 1 mole of N2, 1 in front, comes from 1 mole of this ammonium nitrite. There's 1 in front as well. On top, I have the volume of a gas, and this is volume of N2 in dm cube. So I divide by 24 dm cube per mole. This gives me the mole of the gas, the mole of N2, divided by the concentration or the volume. I'm going to multiply this by 10 to the minus 3. You must know what to do on your calculator to get this time 10 to the minus 3. It basically means 25.0 divided by 1,000, but this is part of O-level, mathematical skills, so you must know these particular, what do they call this? They call this standard form, if I'm not mistaken. So you must know how to press this on your calculator. Yeah, times 10 to the minus 3. It means divide by 1,000. I convert the volume from CNQ to dm cube, multiply them by the concentration, 0.150. So what I can do is I can move this up. Then I get volume of N2 over 24 equal to 25.0 times 10 to the minus 3 times 0.150. Of course, anything multiplied by 1 over 1 is going to be itself. So volume of N2, by right, I could really just move up the 24 straight away, but I decided to do it another step. So whatever you do, do not have times 24 and then divide by 24 here. That is just mathematically wrong. Actually, what I'm going to do is I'm going to cross out the 24 here, and then I'm going to time 24 because I moved out the 24 up there. All right, so I just do it in 1 step rather than 2 steps. What do I get next? I just need to press my calculator. So 24 times 1 over 1 times 25.0. times 10 to the minus 3. Make sure you know how to press your calculator correctly. So that is 0.09. However, the data given, 1, 2, 3 significant figure. 1, 2, 3 significant figure. My calculator cannot think. I have to be a little bit, thoughtful and, think for my calculator. This is the volume in dm cube because this was what I used, divided by 24 dm cube per mole. The unit must match. I cannot have a mismatch of unit. So that is the volume of N2 to 3 significant figure. Appropriate number of significant figure is based on the data that you have used in your calculation. It's all part of scientific skills, and you will have done similar things in physics as well as biology also. Next up, this is not a calculation. This is just, 2 marks is pretty generous for constructing equation, which has to be balanced. Calcium nitrite, as has been given to you, ammonium nitrite, NH4 plus, NO2 minus. So we know nitrite is NO2 minus, not a surprise there at all. I want calcium nitrite, so there's plus 2 minus 1. So we crisscross the valency, just the number there. So it means 1 of calcium 2 plus, you need 2 of the NO2 minus. You get a water and you get a gas. This gas turns damp red lemon pepper blue. It comes from ammonium ions and it reacts with hydroxide. Not the first time you have seen this because this is in your qualitative analysis, as well as when we did this, when we did ionic equation. This will form NH3 gas plus H2O liquid. We know that this is a classic ionic equation for what happened when ammonium ions reacts with any hydroxide. In paper 3 practical, you use sodium hydroxide to react with NH4 plus salt, and you can get this gas which is pungent smelling, and you test for the gas using damp red litmus paper. Damp mean a little bit moist, a little bit wet, and it will go from red to blue because it's an alkaline gas. So what happened here is this loses the H plus and this gain the H plus. I think I made a mistake in my previous tutorial videos on qualitative analysis, so make sure you know that when something loses a H plus, it's acting as an acid because acid is a proton donor. Okay, donates protons, whereas this one is acting as a base because what it does is it acts as a proton acceptor. I've called H plus proton because there's no electron in H plus, there's no neutron in H plus, there's just a single proton in the nucleus of the atom. That is atomic structure. Okay, so what do we have here? Let's write our balance equation. So we have NH4NO2 plus calcium hydroxide, and then I get calcium nitrite, and then I get NH3, and I also get CO2, not CO2, but I get H2O as well. So I have 2 of that nitrite, so I need 2 of that NH4NO2. I have 2 ammonium, so I'll get 2 ammonia. I have 1 calcium and 1 calcium. I have 2 oxygens. The oxygen here is balanced, 2 of nitrite, so I have 2 extra oxygens. No oxygen, I need 2 oxygen there, so 2 H2O. Having said that, I have 4 hydrogens. I have 2 hydrogen here and NH4 plus. Each of them loses 1 H plus, so 2 of them loses 2 hydrogen, 2 hydrogen, 2 hydrogen, 4 hydrogen. This equation is balanced. They haven't asked for stat symbols, so balancing equation is good enough here. Question 6. So what do we have here? We have lithium sulfite, Li2S. They want the formula and want the particles. They haven't mentioned what particles it is, but we know that this is a giant ionic lattice structure, and you should know how to describe giant ionic lattice structure. You have alternating positive and negative ions, very tightly packed because in the solid state they can only vibrate about fixed position. If you cannot visualize this kind of thing, I'm sorry that you haven't really mastered your structure and bonding from your year 9 topic earlier on a couple of months ago. So what you have is the ions, Li plus and also S2 minus. S come from group 6. Group 6 form 2 minus ions, whereas lithium comes from group 1. So what you have is a Y plus cation. They lose 1 outer shell electrons. This one they gain 2 outer shell electrons because both of them want to achieve the noble gas configuration, which is fully filled outer shell. Now they say explain in terms of structure, why does it have high melting point? So they haven't mentioned structure and bonding, but it's always structure and bonding. What is your structure, and then what is your bonding? So I'm just going to copy that. So Li2S has, what is your structure? Your structure, as I mentioned previously, is giant ionic lattice structure. So therefore, melting Li2S, what do you need to break? Needs to break strong ionic bond. What is ionic bond? Ionic bond is the electrostatic force of attraction, so between something positive and something negative. So this is between the oppositely charged ions. What oppositely charged ion am I talking about? I'm talking about the particles from the first part of the question, which is Li plus and S2 minus. I have to break them apart to make them, having spaces in between, because liquids can flow. Liquids particles are not tightly packed, they are simply closely packed with a little bit of spacing in between. The ions become free to move. That's why liquid ionic compound can conduct electricity, but solid ionic compound cannot conduct electricity. Question 7. So for 3 marks here, we don't need to know what is ethane diaoic acid. We just need to know how to do the calculations. So the MR equal to 90. You can sum them up if you want to, but then you can see that they want the atoms of carbon. So I have, what do I have here? I have 1 carbon and 2 carbon. So in 1 mole of HO2C CO2H, there are 2 mole of carbon atoms. If you don't want to use mole, you can think about in 1 molecule. So you can think about in 1 molecule of it, you can count 2 carbon atoms. There are 2 atoms of carbon. So it really depends on which terminology you use. If I use 1 mole, then I use 2 mole of atoms. If I use 1 molecule of that, then I have 2 atoms of carbon. Anyway, what do I know? I'm given the mass of it. So first of all, I think I need the mole. The mole of the ethane diaoic acid is 0.18 gram divided by 90. So mass divided by MR shouldn't be too difficult, I hope. So my calculator showed me 2 times 10 to the minus 3. Okay, make sure you know what this one means. It means 0.002. Okay, but you also need to know how to press this on your calculator and not misread it. If you cannot read your calculator, I'm sorry that you have already lost the game. Then how many atoms of carbon? So we know in 1 mole of it, there's this much carbon atoms. So therefore, the mole of carbon atoms is equal to 2 times the mole of the acid, because in 1 mole of it, there's 2 mole of these atoms. So the mole atom is going to be 2 times however many mole of the acid. Then you get 4 times 10 to the minus 3. The mole of the acid being 2 times 10 to the minus 3 times 2, I get these. When I have the mole of carbon atoms, I need the actual atoms of carbon. I need to relate this to Avogadro constant. Avogadro constant, L equal to 6.02 times 10 to the 23 particles. Could be atoms, could be ions. In this case, it's atoms. And this number is stated in your syllabus as well. That's why they don't give you here in the question, because you're supposed to know it, right? So what happened here is the number, sorry, not mole, but the number of carbon atoms is going to be the mole of carbon atoms multiplied by L. So that's just 4 times 10 to the minus 3 times 6.02 times 10 to the 23. I get on my calculator 2.408 times 10 to the 21. Looking at the data given to us was 2 significant figure, 2 there, 2 there. I have used 3 for my Avogadro constant, but looking at the data, I think 2 or 3 significant figure would have been okay. I mean, it's really down to personal choice, but it's just based on the evidence given. 3 significant figure there, 2 significant figure from the data given. So I'll just say I run it up to 2 significant figure. So I don't think you get penalized here if you do 2 or 3 significant figure, but not 4 significant figure like this on your calculator. Okay. Question 8, so we have transition element. We need to state how many occupied electron shells in the atom of silver. So if you look at your periodic table, so this is about reading straight from your periodic table. So you have hydrogen to helium, there is your first shell. And then lithium all the way to neon, there is your second shell. Sodium all the way to argon, there is your third shell. Potassium all the way to krypton, there is your fourth shell. And then rubidium all the way to xenon, there is your fifth shell. And then where is silver? Silver is your Ag. So silver comes somewhere there. So you know, it is somewhere in between the fifth shell. So you occupied up to the fifth shell. So it's number 5 there. 5, or you can say 5. Occupy up to the fifth shell to fill up to silver. Now describe with the aid of a diagram metallic bond in silver. So this is metallic bonding. This is element. Element means it only consists of one type of atoms. In this case, you only have silver atoms. But within the metallic bonding structure, you have the positive ions. So what happens is you have the positive ions, and the positive ions are surrounded by a sea of delocalized valence electrons. By right, all my cations should be the same size, so ignore the slightly different sizes. Let me just draw this to be a bit more representative. All right, so what happened is I have to label. This is a delocalized. This is a sea of delocalized. Make sure you know these are just valence electrons. They are not all your electrons. And these are your cations. So you do not have anions, but you have something which is negatively charged as a result of the metal delocalizing its valence electrons. So what happened is a metallic bond. So you got to describe metallic bond, right? So metallic bond is the electrostatic force of attraction stated in the syllabus, right? Electrostatic force of attraction. So electrostatic means something positive attracts something negative. So it's between the positively charged ions, and this is of silver, and the negatively charged electrons, and the negatively charged sea of delocalized. So localized means they are fixed, they cannot move, but then they are no longer in a fixed shell. They are now delocalized, they are now free to move. That is why metals can conduct electricity due to the movement of electrons, whether they are in the solid state, liquid state, or whatnot. Okay, so you have delocalized valence electrons, so make sure you do complete that. You see, for that 3 marks, you really need to know how to draw and label these kind of things and put it into words very, very carefully there. Next up, we have observations. This is acidified aqueous silver nitrate. We use it to test for halide. In this case, we are testing it for iodide, but you know you can also test for chloride, bromide, iodide. So you add nitric acid in order to prevent any false positive, because silver carbonate is also insoluble, and then we want to add nitric acid first. We don't see any effervescence, it means it is not carbonate, therefore whatever precipitate we get must be from the silver halide. All right, then you add AgNO3 aqueous. So the idea of writing this aqueous means I don't have to write it in words, using solution. So what happens is I get a white precipitate, white PPT. Of course, you are not allowed to use abbreviation in a theory paper. Only in a practical paper 3 you're allowed to use that abbreviation. Okay, so white PPT, cream PPT, and yellow PPT. And in terms of the ionic equation, so obviously whether it is chloride or bromide or iodide, they're going to give you the silver halide, which is AgCl, AgBr, AgI, and there'll be a solid. This is your classic precipitation reaction, and how you write the ionic equation typically is asked in a practical paper or even in theory paper. They want observations here, so we just need to write down observations. You get a yellow precipitate. Make sure you can spell that properly. PPT is not allowed in a theory paper. Okay, yellow precipitate forms, or you can say yellow precipitate is observed. Question 9. So what do we have here? We have propanoletanoid. Doesn't matter, it is whatever is given here. So let me just say this is P. Let this be P. I can't be bothered to write down it in full detail. So we prepare between a carboxylic acid and an alcohol. So this is the carboxylic acid and this is the alcohol. In an experiment, we use this much of the alcohol, we use excess of the acid. So because we use excess of the acid, we are not going to involve the acid in our mole calculation. So this is our product P. As I said, let this be P. And of course, you kick out water as well. The experimental yield means how much you actually get. So this is how much we actually get. How much we actually obtained or we actually get. Relative formula mass is just another word of saying MR. So the MR of the product P, propanoletanoid, is 100. I got to show that the maximum possible yield, so that means assume 100% reaction. So whatever on the left will go to whatever on the right. I got to assume 100% reaction and show that the yield of that product P is 20.0 gram. So we know the alcohol is used up because that is limiting since the carboxylic acid is in excess. So I need to work out the number of atoms because I need the MR of this alcohol since I'm only given the MR of this product here. So I have 1, 2, and 3 carbons. So the MR of the alcohol, in fact, the MR of the alcohol consists of 3 carbons. So C3, H1, 2, 3. So let me use a different color. 1, 2, 3, 4, 5, 6. So there's 6 hydrogens and there is 1 oxygen. So there's the MR of C3H6O. There is 12 times 3 plus 6 times 1 plus 16 times 1 for the oxygen. So I get 58. What next? After I got the MR, so I think I can maybe save up a space there. Yep, that should save me up some space. So you got to think about the availability of the space. So basically the space that you're given. All right. Anyway, so we have the mole of the product is to the mole of the alcohol. If we look at the balance equation, 1 mole of the product is obtained from 1 mole of the alcohol, so it's 1/1. I have the mass of the product, which I want to show based on a 100% reaction. So 1 mole of alcohol reacts completely to give you 1 mole of product. However much of the alcohol, which was 11.6 gram of the alcohol, divided by 58. So there's the actual mole of alcohol that reacts, should give me the maximum yield of that product P here. And then there's divided by the MR of that product P, which is 100. Mass over MR, give me the actual mole of product. Mass over MR, give me the actual mole of the alcohol that reacted. And of course, then I just move that up. Then I get mass of P over 100 equal to 11.6 over 58. And then what I can do is I can, move up the 100 straight away. Some students like to keep the divide by 100 and then they do times 100. That is mathematically incorrect. So do not ever do that. So there is just times 100 there. And you can choose to do it one more step, or you can choose to do it straight in one go as I did here. So the mass of the product there, 100 times 11.6 divided by 58. I get 20 on my calculator. 3 significant figure, 1, 2, 3, 1, 2, 3, 1, 2, 3. So 20.0 gram, 3 significant figure as shown, as required for that 2 marks. You gotta be able to get to this MR, and you gotta be able to show in a stoichiometric relationship that how to get the 20 gram to get the full 2 marks there. Next bit of the question, calculate the percentage yield. So percentage yield means how much do you actually get divided by how much you expect to get. This is how much you actually get, 6.72 experimental yield. You expect to get 20.0. So 6.72 gram divided by how much you expect to get. And it's a percentage, so I need to multiply by 100%. And hopefully you can see the mathematics, gram and gram cancel. I get 33.6 gram. Previously I had everything to 3 sig fig. They didn't mention how many sig fig, so I just leave this as, oops, sorry, it's not gram, it's percentage as I mentioned, because I already times 100%, the gram has been lost out. Okay, so include percent in your unit as well. So that's the end of that question there. In this next question number 10, so these are typically not the type of questions you will find in a structured paper for O-level or IGCSE chemistry theory paper. Instead, you'll find this type of questions in alternative to practical. This was what I meant by like the paper 2 structured component for this end of year assessment. It's not exactly the same as a real O-level theory paper, because we haven't covered enough topics to come up with that kind of section B question. Anyway, it's still a theory level question regardless, so this should still be useful to assess understanding for all the topics we've done so far in year 9 for these 5070 component or IGCSE extended chemistry component. So we have these burette, so these are burette readings. And then we know that burette readings for O-level or IGCSE is to 1 decimal place. That's very, very important, not just for practical, but also for theory components like this. So our burette has a tab at the bottom. We open the tab and the solution in the burette will come out. And when the solution comes out, that means this level will drop. So this means this is at the initial level, and then this is the final volume, because you allow some of this solution to flow into the conical flask as well. That's what you would do when you're doing the actual titration. So always read the heading whenever you label your table in a theory paper. It depends on your label really. If you put down initial here, then you write down the initial volume. Since this one has listed this as final burette reading, so this is the final burette reading. This is 24, this is 25, well 24.0, 25.0, so there's 24.1, 24.2 because the reading increases downward. So there's 24.2 cm cube. So I do not have to write down the units because the table headings already included the units. So very important that you always have units in your heading or in your labels. Initial burette reading started out from 0.0 as seen here. So do not try, and go fill up the rest of the table before you actually calculate the volume required. This is the same skill as when you actually do a practical, because the first one is typically a rough titration. Although, I mean, it's not implied here that the first one is a rough titration. If you are doing, well, in fact, all of you have done at least one full titration practical, so all of you would have encountered the idea of a rough titration so that you know where you are fishing, okay? So the second titration, so this is where you start, so this is your initial. As you could see, the volume decreases, well, it goes downward as you allow the tab to open, and then now you have a final reading here. So the initial reading is 24.1, 24.2 cm cube, and your final reading, that's 47, that's 48, so 47.1, 2, 3, 4, 5, 6, 7, 8 is also 2 lines above 48, so that makes sense for it to be 47.8 is lesser than 48, is more than 47, you read it downward, 47.8 cm cube. So I got 23.6 on my calculator. And then the next one, this one has been refilled, 1.1, 1.2, 1.3. So initial volume 1.3, final volume 24.1, 2, 3, 4, 5, 6, 7. So that's 24.7. So 24.7 minus 1.3, I got 23.4. This is not a very good set of results, because if you are in a practical paper, you want this difference to be as close to 0 as possible, because you want to be as accurate as possible. When I said that this plus minus 0.2 cm cube, this is the accepted margin of error. Okay, so these are error margins. When you're doing an actual accurate titration, you want this error margin to be as close to 0 as possible. You don't want it to be any difference at all, wherever possible. But then based on these results, these two are the ones that are within plus minus 0.2, so they are where we put our tick on. Alright, so based on the best titration results, when you go on and do your actual practical, you do not always try to achieve this. No, you don't. You want to try and achieve as close as possible, meaning to say as exactly the same as possible. Now you got to calculate average volume based on your best titer, so 23.6 plus 23.4. So make sure you use bracket to prevent any mistakes, any unwanted mistakes, and your final average volume should be to 1 decimal place. As you know, that's what the burette reading accuracy is to in your O-level or your IGCSE chemistry. You see the unit that has already been given. If it is not given, you always have to write down the unit like that. Next up, we are given this NaOH that was in the conical flask. So volume in cm cube, this is mole per dm cube. N equal to CV, your V must be in dm cube in order to cancel out the per dm cube of the unit for concentration. So the mole of NaOH is going to be 10.0 divided by 1,000. Divided by 1,000 is the same as times 10 to the minus 3. You must know how to key this into your calculator because it's part of mathematics in O-level as well as IGCSE level chemistry. If you can't do that, unfortunately, there will be a lot of things you can't do in physics and in math and also in chemistry. I've decided to run out my answer to 3 significant figure because here you could see the data 1, 2, and 3, 1, 2, and 3 significant figure. So what is appropriate number of significant figure depends on the data that you are working with. And that's something that your calculator cannot do. Calculator cannot think. You have to depend on your own brain in order to think about what is appropriate. That's called decision making. So now what is the mole of H2SO4 that react with that much NaOH? Well, from the balance equation, you can see the mole of H2SO4 is to the NaOH is 1:2. 1 mole of H2SO4 reacts with 2 mole of NaOH. If you got them the other way around, this will be 2/1. Doesn't matter. It follows your label. It follows your label always. This is the mole of NaOH that actually reacted. So I'm going to put this in here. And this is the mole of H2SO4 that actually reacted with this much mole of NaOH. So I'm just going to move that up. So hopefully you can see the mole of H2SO4 is equal to a half times 1.00 times 10 to the minus 3. So the previous answer times half, I get 5 times 10 to the minus 4 mole. Again, your calculator cannot think, so you have to try and get to appropriate number of significant figure based on the data, based on the question. Alright, so 10 times 10 to the minus 4 times 10 at 5.00. Now, what is the concentration of the H2SO4? So the concentration of H2SO4 is the mole of the H2SO4 divided by the volume. The volume of the H2SO4 was from your titration volume in the burette. So that's 23.5 cm cube. I have to convert that into dm cube times 10 to the minus 3 will convert cm cube to dm cube, or you could do divide by 1,000. It's the same thing. So this is the mole of the H2SO4. So mole divided by dm cube, that is the unit for concentration. So I get 0.021277. We need our final answer to 3 significant figure. That is as what the question has instructed us, 1, 2, and 3. That is more than 5, so 0.0213 mole per dm cube is going to be our final answer there. Question 11, so this is about titration, but not really. It's about preparation of salt. This is about making soluble salt. So you want to prepare a pure sample. Sodium chloride is our table salt. We know it is soluble in water. So part of that method involved doing titration. Titration between something and something to get sodium chloride. So sodium chloride is a salt. The chloride salt means it comes from hydrochloric acid. As I mentioned earlier in one of the questions on salt, sulfuric acid gives you sulfate, nitric acid gives you nitrate. So we're going to do the titration. We're going to reach an endpoint where we know the endpoint by using indicator. But because you want a pure sample of this, you don't want an indicator. You have to repeat the titration. That's why this is with indicator. But then we want pure. Sodium chloride, so we don't want any indicator. So repeat titration with the endpoint value. but then without indicator. So you have seen this in one of your planning exercise on making soluble salt. I think there was a separation technique, planning work 1. You can find out from that tutorial. You should have done your correction always, because you're never going to learn unless you correct a mistake. Okay, so this is without indicator. So obviously, usually the titrations, we feel that the solution for the conical flask, we usually don't use measuring cylinder. So usually we will use a pipette to measure out a fixed volume. So measuring cylinder is not very accurate at all. So obviously, how do you improve the accuracy? Well, use a pipette. You can even use a burette as well if you want to. So use a pipette or burette. But whatever you use, make sure you can spell it properly. These are all technical terms. They are included in the syllabus, in your lesson notes, in your lesson exercises, in the assignments, in the tutorials, in everything we cover so far. We've emphasized on the working as well as the spellings of all these technical terms. Okay, so use a pipette or burette to measure out the NaOH, the aqueous sodium hydroxide, because that was what you used the measuring cylinder for. Describe what the student does in step 2. So step 2 was the actual filling in the burette. We can assume that the burette has already been rinsed with the solutions. If you are worried, you can say you rinse the burette with a little bit of solution B. Of course, then since we know that is NaOH in here, we know that we know that we are filling NaOH aqueous in here, and we want sodium chloride, so we need HCl aqueous in there. And of course, this is the burette apparatus. We need to fill up the burette up until a certain non-volume. Then we record the volume before we do a titration, initial volume, and then we can start doing a titration with indicator, etc., etc. Okay. So include the names of apparatus A and also solution B. So apparatus A is burette, and solution B is just your dilute hydrochloric acid or dilute HCl, whichever one you like. If you know the formula, it's fine. You can use the formula. If you don't know the formula, well, you should know the formula. I mean, it's part of your common knowledge, right? Okay, so in terms of description of what the student does, so the student, assuming it has been rinsed, assuming the burette has been rinsed with the solution B. So that is what you would do in a real practical, right? You will rinse a little bit of it, rinse with solution B. So you don't just wash away water, you have to rinse your solution B, because water can dilute whatever, distilled water can dilute whatever amount of B that you put in there. That's why you have to rinse it finally with solution B before use. After that, we got to fill up the burette with the dilute HCl, meaning solution B. Okay, record this volume as the initial volume. Okay, this could be 0.0 cm cube, or any other sensible volume, or any other sensible meaning to say you expect your endpoint to be around, I don't know, 25, 30, 35. So you are not going to start your titration volume, initial volume at 45 cm cube, right? So it could be, usually we start with 0.0, but it could be any other sensible starting point for your titration. Okay, so I hope that makes sense there. Identify what is added before you start the titration. So obviously you need an indicator. So this indicator could be methyl orange, as you know. So methyl orange in sodium hydroxide, because you have sodium hydroxide, which is a base in here. So methyl orange in base would be yellow, and then at the end point it will be orange. If you go to red, it will be acidic already. Or you can use phenolphthalein. Phenolphthalein is going to be purple, well, not purple, but pink in alkaline, and then like when you get to the end point, it's just going to go from, you know, one drop of that thing at the end point, it's just going to go colorless like that. Okay, if you can't spell any of these, I think indicator will be all right there. In step 4, the student adds solution B to sodium hydroxide until the endpoint is reached. The student records the volume of solution B added. How the student knows when the endpoint is reached? Well, that's why we use an indicator, right? When the indicator changes color. Indicator is there for you to tell, you know, when you reach the end point, because, you know, the original solution B, dilute HCl, is colorless, the aqueous sodium hydroxide is colorless. That's why we have indicator to change color to tell us it's the end of the end point. And of course, when you want to make the pure salt, you're going to repeat the titration using the exact endpoint volume, but then without adding the indicator, because, you know, there's the exact volume required to reach the endpoint, the neutralization point. So the rest of the method involve adding the recorded volume of solution B to another. This one, another, is no indicator, because you know you will reach endpoint with that recorded volume anyway. So the substance added is not added because that is your indicator that you added previously. Why is it not added? Because we want pure. We want pure sodium chloride without any indicator. Without any indicator present, because you could also say that indicator would be hard to remove. Indicator will be difficult to remove from the solution. So obviously you need other techniques in order to separate out what you want from the indicator then. Okay. Now, the last bit of the question, this is part of a fixed assay questions. How do you get pure, how do you get crystals from the solution in the conical flask? So this is not filtration, this is just after titration. You have the exact volume, so you just don't have excess NaOH, you don't have excess HCl, it's just at the end point. Okay, so what we do is, to the solution, so it's not the filtrate, yeah, be careful. We are not doing filtration for this reaction, we are doing titration. To the solution, concentrate it. So concentrate it meaning to say by heating it until we get saturated solution. By heating it until a saturated solution is obtained. So earlier in this paper, you were asked on the definition of saturated solution. So it's basically a solution where you have the maximum, where you have the most amount of solute in a solvent at a particular temperature. So until saturated solution is obtained. Then what happens is allow the solution to cool, allow the saturated solution. So there's no crystals, no solid at this point. Only when you cool it, then crystals will form. If you heat it until solid is formed, I'm afraid you already heat it too much, you're not going to get crystals, okay? You're just going to heat it to dryness. Then crystals will form upon the slow cooling. You want to get pure crystals, you don't want together with a little bit of the solvent. So what happened then is filter the crystals, but then you still have got a little bit of the saturated solution. So you got to wash with cold distilled water, because you don't want the crystals to dissolve again, so you use cold distilled water, and then you dry. So they didn't mention about dry crystal, they just said pure crystals, but then drying is sometimes asked as well. So it doesn't hurt, you know, if you say dry crystals in between filter paper. You don't get marks here, but then sometimes they do want you to say pure dry crystals. So, you know, that's how you get all the 3 marks for this question. Just describing the crystallization assay. That's the end of that 10-mark question there. Question 12, so this is about rate of reactions. So rate is about how fast the reaction is. You see this reaction in terms of gas production, where we collect the gas by using the displacement of water. So this was filled out with water up to the very top. Measuring cylinder has got graduation. Graduation meaning these lines that allow you to read the volume displaced. When it displays the water, it's going to tell you the volume of the gas being produced. This is a metal and acid. As you know, metal plus acid will give you salt. Here you get metal plus hydrochloric acid. So obviously you get chloride salt, which is metal chloride. You also get a gas, which is hydrogen gas. These are one of a couple of general reactions that you've got to know. So these are just the different metal you use. You use different mass of the metals, and you have all these instructions. Instead of measuring cylinder, what can you use to collect gas? So this is about apparatus for gas collection. So this is part of experimental techniques for gas collection. You could use measuring cylinder, or you could use a gas syringe if you don't want it to be displaced over water. Okay. Unfortunately, you can't use the displacement of air because you are not going to see a volume, because these gas are colorless. So the downward or the upward displacement of air is going to be very, very bad method. Colorless gas, you can't read the volume if you can't see where they're going. So you need a displacement of water like this, or you can use a gas syringe that doesn't allow the gas to escape. They're just going to push on the piston, and the gas syringe will have graduated lines, graduated lines, meaning to say they can tell you how much volume has been collected. So they did tell you it's hydrogen gas. Just give a test and its result. So straight from your paper 3 study and also your theory paper. So test gas with a burning splint. So a burning splint basically meaning you still got a fire going, or you can say with a lighted splint is the same thing. Lighted splint or burning splint has got the fire going. Glowing splint is the one that the fire has gone off, and you use that to test for oxygen. So what happened here is lighted splint or the burning splint extinguishes. Obviously, because you are forming water, hydrogen plus oxygen form water. What is very, very characteristic is with a pop sound. So the pop sound is as a result of the combustion reaction. So obviously, we say the fire goes off. It does not support combustion because you are producing water, and we use water in order to put out fire. So extinguishers mean the lighter splint, the fire gets put out with a pop sound. On to the next question. So we have a series of tests. This is a qualitative analysis, so nothing to do with numbers, but all those tests for cations, anions, gases, as well as flame tests. They are all in the table given in practical paper. But as I told you repeatedly before this, none of these will be ever given in a theory paper, including alternative to practical. There's your paper 4 in all level. So in terms of any gases that you are forming, you need to name it. All right, it's part of your conclusions. And before you name it, you need to identify it. So you need to know the test, the positive result, and therefore what is the gas form. So in this first test, we have aqueous ammonia. So this is very similar to those tests with sodium hydroxide, test for cations. We get a green precipitate. This is insoluble in excess aqueous ammonia. Your conclusion is not just one thing. Green precipitate does not tell you anything at all because it could be, so it could be the Fe2 plus aqueous, or it could be the chromium 3 plus that is present. It could be either that are present, and you have to use sodium hydroxide in order to confirm whether it's iron 2 hydroxide or it's the chromium 3 hydroxide that's actually forming, because in a small amount of ammonia, even in excess, you're just going to form iron 2 hydroxide, chromium 3 hydroxide precipitate, both of which are green. Now when you add aqueous sodium hydroxide, you get a green precipitate, but this is soluble in excess sodium hydroxide. What you're going to get is you're going to get green solution. Solution means the precipitate dissolved to give you a green solution. Therefore, chromium 3 plus is present because iron 2 hydroxide, FeOH twice, this is a green precipitate, insoluble in excess sodium hydroxide, Of course, you know this because you're supposed to know all the results in the table. Now, when you warm it, you have excess sodium hydroxide, remember? So you have hydroxide plus something else, and then you get a gas which turns damp red litmus paper blue. So that gas is definitely ammonia gas. So what happened is they give us the test. The test is, you know, a pungent gas. It turns red litmus paper blue. So the gas is NH3 gas. So I haven't added any aqueous ammonia. This is with sodium hydroxide. So what is this question mark then? What ion does this test? Okay, so NH4 plus is present because this is the test for ammonium ions. When you have ammonium ion plus hydroxide, you get NH3 and you also get H2O liquid. And I've talked about this in the earlier questions. So it's quite unusual that in a real O-level paper that you will get similar concept that get repeatedly tested. But because this is year 9 and we've only done a couple of topics, that's why you see the questions keep on coming up, the same concept keep on coming up again and again. And that's why if you fail to master the syllabus, that is when you know, however the question asks you, in whatever format the question asks you, you will still be unable to do it unless you know what the syllabus wants you to know. Next bit, you add some excess dilute nitric acid to the mixture. We are supposed to write down the observations. Then what do we have in our conclusions? CO3 2 minus ions are in the mixture. So we need to identify the gas because CO3 2 minus reacts with acid. Nitric acid is an acid and it reacts with carbonate. So H plus reacts with carbonate and you're going to get effervescence and you get H2O and you have to balance these equations, aqueous, gas and liquid. This is a common ionic equation. You learned about ionic equation a few months ago when you did balancing chemical equations amongst the many general equations that you're supposed to know. So what do we see? We get effervescence. Effervescence meaning you have a lot of bubbles, rapid bubbling. So this is a V, effervescence. Hang on, let me just write that again. Effervescence. Am I correct? Yeah, maybe. Okay, if you don't like the word effervescence, you see rapid bubbling. Rapid bubbling is observed or was observed. So that means there is a gas, therefore you have to test for the gas, all right? So the gas turns lime water milky. So lime water is a saturated solution of calcium hydroxide. You turn milky or you turn cloudy, that will be acceptable, but milky is typically the one that is stated in the test. So we need to identify the gas just like we identified the gas in the previous question. So the gas is carbon dioxide. And carbonate is present, test for carbonate, add some acid, and then you get some effervescence or rapid bubbling. Next up, you follow. Then you do that in order to rule out carbonate, which in this case you can't rule it out because it is present. And then you use excess of it. So that means all the carbonate has reacted. There is no more carbonate present. If there is carbonate present, silver carbonate will give you a precipitate. But here, there is no more carbonate since you use excess acid. Therefore, the iodide here is a result of this positive test. When you use silver nitrate, you're going to get Ag plus aqueous plus the I minus aqueous, both of which are colorless. And you will get a solid coming out. And you get yellow precipitate. So I should say yellow precipitate forms. So that's the color of silver iodide. So yellow precipitate forms. You should know that this is a classic precipitation reaction. This is the ionic equation for this precipitation. Next up, final question of this paper. You want to test for sulfate. So you got to think back on how you test for sulfate. We always have to add it a little bit of nitric acid first. So add dilute nitric acid. In fact, we know that there was excess carbonate. We know that there was carbonate present. So I'm going to use the exact same condition. I will use excess dilute nitric acid. So add excess dilute nitric acid. And the same reason was why I added excess nitric acid here is so that I can rule out carbonate being the precipitate that I'm forming. So I try to test for sulfate. I use excess dilute nitric acid here. I will get the effervescence. Once the effervescence is over, then I add aqueous barium nitrate, or you could use barium chloride, both of which are aqueous solutions. So barium chloride, I could also use barium nitrate, whichever one you want, but it has to be aqueous solution. Then what happens is you get a white precipitate. Because we already ruled out the carbonate, since we already reacted all the carbonate, the white precipitate form here is a result of the barium sulfate. So this is a second very classic precipitation reaction, which not too sure if you've seen in this paper, but is one of the classic ones. Barium aqueous and then SO4 minus aqueous. They precipitate out this white precipitate, very commonly asked in O-level as well as beyond O-level and also IGCSE level chemistry. So that's the end of this year 9 assessment. It's a paper 2, but I've incorporated personally some alternative to practical because of the limited number of topics we have done in year 9 so far. So if you got any questions, feel free to leave a comment, or if you're my students, feel free to text me and ask if you don't understand any of this. Although you have been informed in advance that you're supposed to master the syllabus in and out. Every single thing in the syllabus you have to master it, because Cambridge says they can ask you anything that's in the syllabus. Thank you for watching, and do subscribe to the channel. Click the button on the bottom right to do that, and follow me at ptet.chemistry. There's ptet.chemistry on Facebook, Instagram, Twitter and Telegram to get connected and to get notified about future updates. Alright, thank you for watching. See you in the next tutorial video.